Hello everyone, and welcome back to the Mathlete Academy. Today we will be going over Chapter 12, or Probability, in your textbooks. Probability is just the study of the likelihood of an event occurring. It's from a scale from 0 to 1, being inclusive of these values. So just say something like a coin flip. Each side has what's known as a 0.5 probability of showing up. This is also can be written as 50%. And we'll get into why this is later. But yeah, each side has a 0.5 probability of showing up, and this is in the range from 0 to 1. Again, this can also be written as a percentage. So when we're dealing with probability, we have to have what's known as an experiment. And in an experiment, we'll have a series of outcomes known in probability as a sample space. So let's just say we have a sample space containing, so when you're running a sample space, you just have to put your individual values that are in your sample space inside these brackets. So let's just say we have 1, 2, 3, 4, and 5. These are the numbers in our sample space. Now, it doesn't have to be numbers. It can be stuff like colors, like, red. It can be things like dog or whatever. You just have to make sure that all your variables in here are separated by commas, because these are all separate values, and they're inside these brackets. I'm just saying it's not just exclusive to numbers. So this is your sample space, 1, 2, 3, 4, and 5. And now, when these values are in the sample space, all the outcomes for the experiment, if one of these was randomly chosen, are equally likely, as all of these values only repeat once. And the sample space with all equally likely outcomes is always equal to 1 over n. N here represents the number in the sample space. So here there's 5 possible outcomes. So the number in the sample space here, n, equals 5, because there's 5 possible outcomes. You can get 1, 2, 3, 4, or 5 when randomly selecting a number. So the probability of getting just one of these numbers, so just say the probability of getting 1 would be 1 over 5. All right. Now, what an event is it's just an event is just a collection of some of these outcomes being a subset of this sample space. So let's just say we want an event where all the numbers are even. We'll call this event E. So within this sample space, the event is equal to just 2 and 4, because these are the only 2 outcomes which satisfy the conditions to meet E, our event E, or being even, and that are contained within our sample space. So that's what events need to do. They need to be contained within the sample space, and they also need to satisfy the conditions of the event. So 2 and 4 would be in E because they satisfy the conditions of this event. Now, if we were to draw this on a Venn diagram, we would have our sample space out here, and then we'd have E inside it, which contains the set the outcomes 2 and 4, because they are both even. And then out here we would have 1, 3, and 5, because whilst they don't satisfy the event E, they are still within our sample space, so we do have to write them in our box. So also here we'd have right, if you could just cut this bit out when I say also here, we would have, just cut that out when I just go from like here when I was ending this segment. And now we're just going to get on to what's known as probability. So the probability of any event occurring is written as P of that event. So if remember with our E here, our event E back there, we would write it as the probability of E like this. So the probability of any event occurring within a given sample space is always between 0 and 1, inclusive of these values. So it's always the probability of an event occurring, it always lies between 0 and 1, or is equal to 0 and 1 for any event. So here we would write it as probability of E. And now, you may be wondering, how do we calculate the probability? So, as we can see down here, the probability of event is the number of outcomes that are favorable to the event over the total number of outcomes. So, remember over here we have our Venn diagram, where 2 and 4 meet this condition. So we have 2 possible favorable outcomes to the event out of the 5 in our total sample space, 1, 2, 3, 4, and 5. So, saying that all values are equally likely to be chosen, the probability that we choose specifically an even number is going to be 2 over 5, or 2/5. That is the probability of this experiment. So, the total, another thing you want to know is that the total probability of all possible outcomes in an experiment always sums to 1. So, let's just say back here, obviously we have the probability of it being even is equal to 2 over 5. But what about these other outcomes here? So, the probability of it not being even, which is denoted by like this, we'll get into this a little later. The probability of it not being even is 3 over 5, because these are the values that aren't even in this event. And now obviously we have all the different values accounted for in our probabilities, so we add these together, and as you can see, it'll equal just 1. So that's just a proof of this statement down here. Now let's just try some practice problems so that you can get it a bit better. So we have a bag containing 20 red counters, 5 white counters, and 15 yellow counters. The probability that it's red, remember, the probability of any event is just the favorable outcomes over the total number of outcomes. We just wrote it as F over T. So the favorable number of outcomes are 20 over total, which is 20 plus 5 plus 15, which is 40. So the probability of pulling out a red counter is 1/2. Now for yellow, we have 15 favorable outcomes, because 15 of these counters are yellow, and over 40 possible outcomes, so the probability is 3/8. Just remember that this is assuming that all of these values have an equally likely chance of being pulled. That's what we always remember, that probability only is like this when all the outcomes are equally likely. Now let's just check this problem down here. On a spinning wheel, all numbers go from 0 to 36, meaning there are 37 possible outcomes, because we're including 0 in this sample space. So there's 37 possible outcomes. Our sample space would look like this, where we have 0, 1, all the way up to 37. So yeah, not 37, sorry, all the way up to 36. And there are 37 possible outcomes here. Anyway, so when we have the probability that it's going to be an even number, so the probability of it being E, we'll call this event E, is there are 19 numbers in this data set that are even, including 0. So 18 plus 0 is 19 over 37. So this is a probability that we pull an even. The probability that it's an odd number is just 18. This is 18 numbers between 0 and 36 that are odd over 37. And finally, the probability that it's less than 15 excluding 0, we'll call this event C after the question. So the probability of C, there are 40 numbers which are less than 15 and not including 0. So it's just the probability that one of these numbers is pulled is just the number of favorable outcomes, 14, over our total number of outcomes, 37. So now we'll get into some other stuff. The complement of an event, or we can write this as not A, or like this with an A dash, or A C. But the point is, the complement of an event is just all the values which do not satisfy this event. And every outcome in the sample space that is not does not satisfy A, or is not in A. So therefore, when we have the complement event, when we add it together with the event, the probability will always equal 1. And so to find the complement of an event, or not A, we'll just take 1 minus the probability of A. As you can see here, when we have our total sample space, we have our event A here, and then all of this is not A, and you can see how all the values in the sample space are being accounted for. So probability of pulling either A or not A will always equal 1. Now, if we go back to what I was showing you up here, this is just not E. As you can see, the probability of E plus the probability of not E equals 1. And I just showed you already up here. So the probability of not E is just all the values outside this data set. As 1, 3, and 5 do not satisfy the conditions to being an even number, they are in the set of not E. So they are just 3/5, or they're not in the set of E. It's a more accurate way of describing it. So sometimes we have more than one event in our Venn diagram. So for example, here we have event A, and we also have event B. And so event A is a number greater than 5 is chosen. Event B is a number divisible by 3 is chosen, and our sample space is 2 to 12 with 11 different values. So, as you can see here, the numbers in this central part, they satisfy both of these conditions. So we put them in this intersection, also known as A and B. And it could be written like this, because these values satisfy to both of the conditions of A and B. So we write this as A and B equals 6, 9, and 12. You can write, as you can see, just done down here. Now, sometimes we'll also be asked A or B, like how do you find A or B? So A or B is just both the full circles of A and B, because it's just asking for one of these values to satisfy either the conditions of A or the conditions of B. So what that means is that we include both of these circles, and just it's just everything that is within either circles A or circle B is included, and obviously the stuff that's not in neither of these is excluded. So the probability of A or B, so not the probability of A or B, the set of A or B here would be equal to 3, 6, 9, 12, 7, 8, 10, and 11. And as you can see here, there are 8 favorable outcomes that are either A or B. And you write A or B like this, with a little U-like symbol at the bottom. And obviously you can see here, this is what has just been done. I just showed you earlier. So we got A and B in the center here, and then we got A or B is the combination of both of these circles. So sometimes we have an addition rule for probability, where when you want to find A or B, you add the probabilities of A and B, and then you subtract the probability of A and B. This is because when we have a Venn diagram, I'll just prove it to you. We have A here. This is our event A. Then we have when we add the probability of B, we can see that this central bit right here has been accounted for twice, and this central bit is our intersection A and B. So we have to minus one set of this intersection in order to get the true value of A or B, or else this middle section will be counted twice. Two events are mutually exclusive when they have no outcomes in common, meaning that A and B is not equal to anything, and this symbol symbolizes an empty set. So obviously you can see here the two circles are separated. They do not have an overlapping zone, and none of the events none of the possibilities inside A or B satisfies both of these conditions, so there is no intersection. So the addition rule here just becomes the probability of A plus the probability of B if and only if they are mutually exclusive. So we don't have to minus the central intersection bit, because obviously there's no central intersection bit to be found. So now let's just answer a few of these questions. So a card is drawn at random from ordinary pack of 52 playing cards. What was the probability that it's not a king? So the sample space for a king, the event of a king, would be club, spade, diamond, or heart. This is the event K. Obviously, all four of these kings would satisfy this condition. So there's 4 possible outcomes here out of 52. So the probability of K occurring is 4 over 52, because these 4 outcomes are favorable to being a king. And then this is just the total number of cards. And this simplifies down to 1 over 13. So when we're trying to find the probability of not K, we can use our rule from before, where the probability of K plus the probability of not K equals to 1. And you can rearrange it like this. So 1 minus the probability of K will give the probability of not K. So just 1 minus 13. So we get we get 12 over 13 as our probability of not K. Now let's try this equation. This question right here. 100 students, 60 study math, 70 study physics, and 30 study both math and physics. So if we were to represent this information on a Venn diagram, you'd have 2 different events here. We'll label the event in which they study mathematics as M, and when they study physics as P. So M and P. Now, since 30 study both, we put 30 within this intersection. Hold on, I might just make it a little bigger. There we go. So 30 are in this intersection. And then since we have 30 within both of these events, we just have to, when we have 60 students studying mathematics, this includes the 30 who study both. So we just have to minus 30 from our 60 total. So just to get the people who just study math. So this would be 30. So 30 students study math. And obviously you can see here 30 plus 30 will give us 60. And there are 60 students here that study math. And so for physics, it will be the same thing. So 70 minus 30 gives 40. So there's 40 students that just study physics. Now, as you can see here, all 100 students are accounted for as either studying math or physics. So there's 0 in this sample space outside of these 2 events. So now we'll answer these questions down here. So the probability that they study mathematics and not physics. So you just write it like this: probability of math and not physics. We can just shade this area in on our diagram. It's just mathematics and not physics, so we don't count the union. We don't count the intersection. Where the 30 students that study math, this is not counted because they would be a part of physics. So the probability of math and not physics is just 30 over 100, which equals the 3/10. Then over here, the probability of physics and not mathematics is just equal to this shaded area right here, physics and not mathematics. So it's 40 over 100, and this simplifies down to 2/5. And finally, question 3, not physics. So the probability of not physics and not math. As you can see here, outside of physics and math, there is 0 in this sample space. So there's 0 possible outcomes where there's someone is selected that doesn't study math or physics. So we say here that the probability of them not selecting someone who studies neither physics nor math is 0. Just here's time to learn a new concept, relative frequency. This is not the same thing as probability. It's more an experimental form where the number of times an event A occurs divided by the total number of times the experiment is performed. So as we can see here, if we were to flip a coin 100 times and we got heads 40 times, we could divide 40, because that's the number of times heads was achieved and the event was satisfied, over 100 to get 2/5 as an estimate for the probability of getting a head. This is just an estimate of a probability, also known as the relative frequency. This is not the same thing as probability, however. As you can see, for example, if we were to have a coin, it has 2 possible outcomes, and one of which is favorable to the event where we get a heads. So the probability of getting a heads would be 1/2. And obviously you can see here 2/5 is not equal to 1/2. This is because relative frequency is more just an estimate and not an exact probability. So let's try this question where we have Abdul chose a card at random from a not necessarily standard pack of cards. He repeated this process 500 times, and the results of our experiment are in this table. So fill in the missing entry in the table. We have 500 possible cards, and if we add all of these up together, we get that these different categories have had 366 of the cards drawn. So the number of clubs would just be equal to 134. So there were 134 clubs that were drawn. Alright, question B. What is the estimated probability that the next card Abdul withdraw is a spade? So remember, our relative frequency formula is just equal to the number of times that the event was achieved over the total number of trials. In this case, it's 500. So a spade right here. So the relative frequency is just equal to 112 over 500. This is the number of times that the spade was achieved. And this just simplifies down to 28 over 125, which I don't believe can be simplified any further. So for a heart, it's 119 over 500, which I don't think can be simplified any further because 119 is prime. For 3, not a club, as we calculate here, there are 366 times that not a club was drawn. So this is just 366 over 500, which I believe can be simplified down. Let me just get out my calculator for this one. 366. This can be simplified down to 183 over 250, which I don't believe can be simplified any further. And finally, the probability that a red card was drawn. So the red cards are just the hearts and the diamonds, so it's just the sum of these two over 500, because that's the total number of experiments, remember? The total amount of times this experiment was conducted, remember? Sorry, I'm just starting over from Wednesday. So we have 119 plus a 135 over 500. This is just equal to, let me get my calculator out again. 18 plus 1. This is equal to 254 over 500. And now this just simplifies down. If we use our calculator again, this just simplifies down to 127 over 250, which I don't believe can be simplified any further. But we've just been dealing with single-stage experiments. What happens when we have what's known as a multi-stage experiment? So here you can see we've tossed a coin twice, and these are the 4 possible outcomes where we get heads and then heads, heads and then tails, tails and then heads, and then tails and then tails. All of these 4 outcomes are equally likely, so each probability of these occurring has a 1 in 4 chance. A way of experimenting these multi-stage experiments is with a tree diagram where we represent the first experiment being done and then the second experiment, and then we list them at the end right here. So we have heads and heads, heads and tails, tails and then heads, and then tails and then tails. Each of these make up the sample space because these are the 4 possible outcomes, so our sample space is just right here. Each of these have a 1 in 4 chance of being of occurring within this experiment. But another approach we can use is an array diagram like this, where we have where we're tossing a die twice and marking what we got from 1 to 6 on both die and marking all the possible different combinations. So we have tossing each of these numbers on die 1 and then tossing each of these numbers on die 2. And as you can see here, all of the possible combinations have been marked down here in this array diagram. So as you can see, let's just take an entry like 4, 3. This shows that on the first roll, a 4 was rolled, on the first roll, and then on the second roll, a 3 was rolled. So that's just what these different things in brackets are representing. So let's just try one right here. A coin is tossed 3 times. Draw a tree diagram showing all the possible outcomes. So the first time is just either going to be heads or tails. And our second toss, once again, will be heads or tails. And finally, our third toss, heads, tails. And then for the tails side, heads, tails, heads, tails, heads, tails. And then we can write a list of all our possible combinations on the right hand side. You don't have to do this, but it personally helps me in order to see the true size of the sample space. Heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. So this is all of our sample space right here. What is the probability that 3 heads are obtained? There's only one possible outcome which satisfies this condition up here. So there's one favorable outcome out of our sample size of 8. So there's the probability that that all 3 heads are obtained is just equal to 1 over 8. That's a bit messy. Let me just. The probability that 3 heads are obtained is just equal to 1 over 8. Now, what is the probability that exactly 1 head is obtained? So exactly 1 means only 1. So this one, all of these values only have 1 head being obtained throughout our 3 tosses. So the probability of 1 head only equals 3, because there's 3 possible outcomes over our 8 total outcomes here. Finally, D, what is the probability that at least 1 head is obtained? So at least 1 means just 1 or more. So all of these values right here, except the last one, where it's just all tails, have at least 1 head. So the probability that at least 1 head is obtained is going to be equal to 7, because the 7 outcomes which satisfy this over 8. For multi-stage experiments, there's 3 main ways that we can represent it: through systematic listing of all the different possible combinations, as you can see here. through a tree diagram, which you can see here, and an array, which is only suitable for two-stage experiments where we have one variable and then another variable. So it's not suitable for when we have three-stage experiments where we do, for example, like three dice tosses. That would not be suitable for these sorts of events. Finally, something you'll need to know is the distinction between with and without replacement. So let's just say here, a bag contains 3 red balls, R1, R2, and R3, and 2 black balls, B1 and B2. They're chosen at random and their colors recorded, and then we can arrange it in the array as seen here, where red 1, red 2, red 3, and black 1 and black 2, and then for our second ball being chosen, red 1, red 2, and red 3, black 1 and black 2. Obviously, all the possible outcomes are arranged within this array, but something important for this experiment is that when the ball has been chosen, it can be put back into the bag to be chosen again. This is called replacing the value that was taken. Each of these outcomes here is equally likely, so each has a 1 in 25 chance of occurring. So let's A, for example, be the event that both balls are red. We have all of the different possible outcomes where both of the balls are red, and therefore the probability of A here is just equal to 9 over 25. However, when we take the ball out and then don't put it back in the bag, we don't allow repeat events or repeats to happen. So if red 1 is drawn within the first ball, it can't be drawn again in the second ball. So therefore, this is called doing it without replacement. So obviously red 1 and red 1 can't be drawn, red 2 and red 2 can't be drawn, red 3 and red 3 can't be drawn, black 1 and black 1 can't be drawn, and black 2 and black 2 can't be drawn, because when it's drawn the first time, it's not put back in the bag, so therefore we cannot draw it on the second time. As you can see here, this cuts down obviously all the repeated trials where we get the same ball twice, and there's now only 20 possible outcomes that there could be. And so when our event A is that both balls are red, we don't include these 3 here where we got the same ball twice. So it's just these 6 outcomes over our 20 possible outcomes. So the probability of both balls being red is just 3 over 10 now. As you can see, this does definitely change our results. So let's just try with this problem right here. A 2-digit number is randomly created from the digits 3, 4, 5, 6, and 7. So let me just draw up a table. This should be good. There we go. Alright. So this is our first digit. And this is our second digit right here. So our first digits are 3, 4, 5, 6, 7. Second digit is 3, 4, 5, 6, and 7. So we have 33, 34, 35, 36, 37, 43, 44, 45, 47. These are just all the possible outcomes that can be made with forming two of these numbers within our sample space. Oh, not our sample space, sorry, our selection of numbers. Our sample space is just all our possible combinations. As you can see here, we're going to have 25 different combinations that can be made out of these 5 numbers. 75, 76, and 77. There's 25 different combinations here, and this is our sample space. Now, if each digit is allowed to be used more than once, meaning with replacement, which is what we've done here, so where we have 3 and 3, 4 and 4, and so on and so forth, where the same digit can be used twice. So with replacement, now we're just going to find some probabilities. We'll call this probability I after the question. Probability that an even number is greater than 50. So our even numbers greater than 50 are just these and these. So we have 6 possible outcomes, which are greater than 50 and even, and then we over our 25 possible outcomes. Now for our second question over here, an odd number less than 60. So our odd numbers, let's just highlight them, that are less than 60, are just these, and these. So there are 9 possible outcomes over 25. This is our probability right here. Now, however, in the second question, it asks us if each digit is allowed to be used only once. So this is saying without replacement. So therefore, if a number is picked, it cannot be used again. This eliminates our central row, our central diagonal row right here, where we had all the repeated numbers being formed out of 2 of the same digit. Obviously, now that we are doing it without replacement, we can't repeat the same digit twice. So all of these are not going to be possible results. And now you can see that there's only 20 possible outcomes here. So now we'll just try and figure out these two probabilities. An even number greater than 50. So we have these. And as you can see now, 66 has been taken because it's using both 6 and 6, which wouldn't be possible without replacement. So an even number greater than 50, there's 5. The probability of this, there are 5 outcomes which satisfy this over our 20, which just simplifies down to 1/4. Now, divisible by 11, as you can see here, the only numbers that are divisible by 11 were the ones in this replacement band right here, because 33, 44, 55, 66, and 77, they were all divisible by 11, but none of these digits can be formed without replacement, as the digits, none of these numbers, sorry, can be formed without replacement, as the digits cannot repeat twice. So therefore, the probability that this occurs, and none of these are divisible by 11, by the way, so the probability of a number being divisible by 11 in this dataset is 0. Alright, that's just going to be it for this one. I hope you guys enjoyed and you learned something. Signing out. Bye.